Okay. So welcome everybody to this AJS seminar. Today's speaker is Maria Strazzullo from Politecnico di Torino. And the title of her talk is Full Order Model and Reduced Order Model Consistency for Evolve Filter Relax Regularization. Thank you, Maria.
Thank you. Thank you, Francesco, for the introduction. I'm very happy to be here with you today. I mean, this was my previous home, so I'm really happy to talk a little bit about this new line of research that I started actually in CISA. So this is a slide of motivations and outline. I take advantage of this slide to thank my collaborators because this topic is actually really a side topic with respect to my PhD thesis that I had in CISA. So I really needed a lot of help from, experts of the topic. So I thank Francesco Ballarin, Michele Giufoglio, Professor Gozza, and also Professor Traian Iliescu from Virginia Tech that helped us a lot, to reach the results that I'm going to show. Here you have an outline of the talk, but actually I don't want to focus much on the outline. I would like to focus on the motivations. So here there is a scheme about the topic I'm going to deal with. We will deal with Navier-Stokes equation in a convection-dominated regime. Actually, in a marginally resolved regime, it means that basically the resolution of your mesh, it's not enough to capture all the dynamics of your system, okay? And in this case, basically, some spurious oscillations of the velocity can occur, and you need numerical stabilization. Great. However, if you apply standard discretization techniques, this can be unbearable with respect to, computational time. And so you can rely on reduced order modeling to solve your problem for several time instances or several parameters. Great. But now there are two ways to go. So you can stabilize your model also at the reduced level, or you cannot stabilize your model at the reduced level, because actually the reduced order model is built from the full order model that is already stabilized. So it's a natural question to, understand if you have to stabilize or not, and if stabilizing also at the reduced level is beneficial or not. So this is the topic of the talk. We focus on a very specific stabilization, so evolved filter and relax model. So let's start with the problem formulation. As I told you, we work with Navier-Stokes equation in compressible flow. So here I want to find the velocity U and the pressure P in a two-dimensional domain that verify this equation here. You see that I have a Dirichlet boundary condition on a portion of the boundary, and homogeneous Neumann condition on another portion of the boundary. And since the problem is time dependent, you need also an initial condition, for the time t0. The spaces are suitable Hilbert spaces, and here the parameter is the kinematic viscosity. The kinematic viscosity describes how the flow moves. Okay, so if you're not familiar with this equation, basically, if the kinematic viscosity is high, you have a diffusive effect on your system, while if the kinematic viscosity is small, you have high Reynolds. And if you have high Reynolds, it means that your flow somehow is going faster, and it's very difficult to, simulate and reproduce. And in a marginally resolved regime, so if your mesh is not fine enough, basically you can have spurious oscillations. In order to alleviate this problem, you can somehow stabilize your system. And this is the reason why we apply the evolver filter and relax system model, sorry. So we use finite element, P2, P1 finite element for space discretization, and backward Euler formula of order 1 for time discretization, And the EFR algorithm is basically divided in 3 steps. So the first step, the evolve step, actually solves a standard Navier-Stokes equation for time t n plus 1, okay? And it depends on a velocity here, time tn, that somehow is post-processed, okay, in the steps 2 and 3. So now I'm going to show you how to obtain this velocity. So here you obtain a Wn plus 1 that is actually standard Navier-Stokes equation solution. Great. But then what you do, you filter, okay, this solution. Basically, you build a linear system where you are smoothing your solution here through this Laplacian, basically. So you use a differential operator, a differential filter of radius delta. I will be more detailed about the value that you can give to delta later on in the presentation. And in this way, you are somehow smoothing, okay, all the dynamics that happened at the small scale that are not precise because your mesh is too coarse to describe them, okay? So all the spurious oscillation that you have, the high frequencies, let's say, are somehow smoothed out through this parameter here, okay? So the differential filter smooths the input data. Our input data is the standard Navier-Stokes equation. Great. And now you have a third step that is actually a relaxation step, in the sense that your final post-process solution is actually a combination of a convex combination of your standard solution Navier-Stokes equation and the filtered one. Okay, so the parameter chi actually lives in 0, 1. So if chi is 0, basically you have standard Navier-Stokes equation here, while if chi is 1, this term disappears, and basically you have your solution that is filtered, okay, all along. So you see that you have to choose chi in order, you know, with a sort of trade-off in order to maintain some accuracy with respect to the standard Navier-Stokes equation and to smooth out your solution that is not precise. Here I'm showing the mesh that we are using for our numerical simulations in order to let you understand that actually this is, let's say, a mesh that it's not able to capture all the dynamic of your system, but it's still quite fine, you see. So it's cursed for the problem that we are dealing with, but actually the degree of freedom of this mesh is high, and so the simulation can be time consuming, most of all for the step 1. For the step 2, actually you have to solve only a linear system, and the step 3 it's, you know, only a combination of solutions, so it's not so heavy. And this is an important point that it will be somehow important later on in the talk. As I told you, since the system is time consuming, I want to apply reduced order modeling. For now, we focus on reduced order modeling in time, and maybe this slide is a bit boring for the ones from MATLAB group, but you know, the audience, maybe it's not all from the group, so I will focus a little bit on proper orthogonal decomposition. So actually the goal of reduced order modeling is to build an accurate solution, okay, for all the time instances at reduced cost, okay? So the strategy is actually based on a double discretization. So you have your solution at the continuous level, let's say, you apply your full order model solution, okay, so the standard simulation that has a dimension here, you obtain your discretized solution, and now assuming that your discretized solution is quite similar to the continuous one, you can somehow build your reduced order modeling, okay, in what is, I mean, in an offline phase. So we call the building phase offline phase. And then once you have built this space of dimension R, with R much smaller than calligraphic NH, with calligraphic NH, I'm indicating the global dimension of the system, both for velocity and pressure, okay, here in this case. Once you have built your reduced order modeling, then you can project all the matrices in that space, and you can solve the system in order to obtain a reduced velocity at reduced cost. The same holds for P, for sure. So here I'm actually showing the pipeline for the velocity, but the same holds for the pressure. How can I build my space in the offline phase? Okay, so here, as I told you, there is an offline phase where you build the space, and there is what is called an online phase to find the solution. So for the offline phase, I use POD. POD is an exploring compression algorithm. So basically, you look at the solution to several time instances here, okay? And you build the covariance matrix of the snapshot with respect to the L2 product, and you solve an eigenvalue analysis on this covariance matrix. And you know, the covariance matrix is a positive definite, so the eigenvalues are all positive. You can order them, and you take the R largest eigenvalues that are the most representative of the energy of your system. So the eigenvectors related to these eigenvalues are actually a base for your reduced space, and you can use that base to represent at reduced cost your solution here. For the ones who are familiar with this technique, I used also supremizer to ensure the well-posedness of the system at the online phase. Now, as I told you, you can apply the POD. Here there is a pseudocode for the POD for the evolve, filter, and relax problem. But then at the online phase, you can solve standard Navier-Stokes equation. Okay, so you are not regularizing also at the online phase, but you are only solving Navier-Stokes equation. And this algorithm is called EFR, no EFR. But then you can choose also to regularize at the online phase, at the reduced level, and you have EFR, EFR. And as you can see, you apply the POD for, you know, all the variables, and in the end, you solve step 1 at the reduced level, the step 2 at the reduced level, and the step 3 at the reduced level. So now let's start with some numerical results to understand if it's beneficial or not to use this formulation. We are working with a 2D flow pasta cylinder. So this is actually the domain. Here I'm recalling the Navier-Stokes equation that we are using. So in the blue lines, okay, let's say the blue part of the boundary is where homogeneous Dirichlet boundary conditions are applied. Here you have an inlet condition that is periodic in time. I will be more detailed later in the next slide, actually. And then the flow goes here and exits over this part of the domain, okay, with Neumann, homogeneous Neumann conditions. These are all the parameters of the experiments, let's say. For now, the kinematic viscosity is fixed. And then we will move over, we will move forward, you know, in also reduction in this parametric setting. But for now, it's fixed. And then this is my inlet condition. As you can see, it's periodic in time. Okay, so it's a parabolic, but you know, it's periodic in time, and it changes with respect to time. Here you have the parameters of the mesh, so the mesh size. Okay, if you see, I mean, I will be more detailed later, sorry. So let me go through the parameters, through all the parameters here. NH is the dimension of my finite element solution, okay? Delta T, it's of course the time step that I'm using, and here you see the filtering radius delta. So the filter radius now it's fixed for all the experiment at this value. That is the Kolmogorov scale. The Kolmogorov scale is a scale of the mesh, okay, where it's where the smallest case of the mesh where the dynamic of your flow somehow is happening. So you can capture the dynamic if you have the mesh of that size, okay? And it's a classical choice to use the delta, okay, of this order. And you see that our mesh is, you know, if the H mean value of my mesh somehow is higher of the Kolmogorov scale. So in this sense, I am in the imaginary result regime. Okay, the experimental setting actually depends on chi. So in the first experiment, we have no relaxation at all. And in the second and in the third experiment, we have relaxation, but in two different, time intervals. So we focused on two different time intervals. And I will show you some reconstructive solutions and also predictive solutions. So let's start with the experiment. As I told you before, in experiment 1 is the simplest because you have no relaxation. In this sense, chi is equal to 1. And as I told you, if chi is equal to 1, basically your post-process velocity is actually all, filtered. So you don't have, the combination with standard Navier-Stokes equation. However, there is an issue here. If you apply the filter, you are not verifying the incompressible constraint anymore. There is some literature that explain that, but I don't want to enter in the details right now. So here I'm plotting actually the divergence, the average divergence over the nodes of the cylinder. Okay, so I'm taking all the nodes of the cylinder, I'm computing the point-wise divergence, and then I'm taking the average and I plot them for all the time instances here. And you see that the divergence is quite high, most of all for t equal to 4, and you see the divergence value, the point-wise divergence value for t equal to 4 here over the cylinder, the boundary of the cylinder. In order to solve this issue, basically we use another stabilization technique, the grad-div stabilization, and it consists to add a diffusive term, okay, to the step of the filter. Gamma is chosen equal to 100, always looking at some literature. However, there is a lot, of sensitivity analysis that can be done on that, but it went beyond the goal of our results. So we decided to be stuck with the gamma equal 100 because it gave us acceptable values for the divergence. You see here that now we have something that is 10 to the minus 4 for the average divergence, and you see the point-wise also, it's always of that order of magnitude. So we were happy with that. I want to stress that we are not applying grad-div stabilization also at the online level, because the modes have this order of, divergence if you build your problem with snapshots of this kind. So actually we are not applying, once again, the grad-div stabilization. Great. So these are the data for the POD reconstruction. So we took 200 snapshots in this time interval, and we are retaining only two bases for velocity, pressure, and the supremizer 2. And you see that basically with EFR, we are recovering quite well the EFR velocity, while with EFR, no EFR, we are totally off, both in velocity and pressure, as you can see here. And the accuracy can be seen also from the relative errors. So from now on, when I will talk about relative errors, actually, I will talk about the L2 errors, okay, over the domain, and I will plot them in time. So you see that basically for all the time instances, EFR, it's always below EFR, no EFR for the velocity. And also for the pressure, I mean, there is here a peak for EFR, no EFR that is good. However, overall, we are always good with EFR. You see, we are not reaching high values of the error as EFR, no EFR. So we are more accurate. The accuracy will be studied also in the representation of the force coefficients. So the drag and the lift coefficients. The drag and the lift coefficients basically give you an idea on how the flow oscillates. Okay, so it's the drag coefficient is a tangential force over the boundary of the cylinder, and the and the lift is a normal force over the boundary of the cylinder. And you see that basically here, EFR and EFR are quite similar, both for drag and lift, and EFR no EFR is totally off. I want to stress that recover the force coefficients was the most difficult part, let's say, of the results, and you will understand later why. Great, so now I'm going to show experiment 2. Experiment 2, it's a little bit more challenging because now you have the relaxation. So your solution is a combination of standard Navier-Stokes equation and filtered solution. And the snapshots, however, now have small divergence values because you see that in the combination, actually, somehow you are recovering the divergence constraint here. So we do not apply grad-div stabilization in this case because we have divergence values around 10 to the minus 3, and we were happy with that. So the data here, the data are collected here in this table, and we took this time 2,000 snapshots, okay, in the second half of the interval. So you see that we needed much more information in order to recover the solution. And here you see the values for the basis. The values for the basis have been taken always with this criterion. So we wanted to recover the 99.99% of the energy of all the snapshots that we take, okay? And you see that basically EFR, it's quite accurate, okay, while EFR no EFR has somehow some inaccuracy here, okay? In the pressure, I cannot see actually any difference, but here in the velocity, you see that something is going wrong in the vortex shedding behavior here. And EFR is more accurate also in terms of relative errors. Indeed, we are always below the solid blue line, okay, that is EFR no EFR, and you see that we have pretty good errors for the velocity, and we are below also with the pressure. And here there is another plot that is, let's say, a little bit more difficult to read, so maybe we can read it together. This is a Pareto front plot. So the Pareto front plot gives you an idea on how convenient it is to use your algorithm with respect to the time that it takes to be performed and the errors that you have at the end. So here you see the relative wall time basically is the reduced time, okay? So the time of a reduced solution over the time of the full order solution, okay? So being less than 1 actually means that you are having some kind of speed up in your algorithm. And now let us focus on the orange stuff, so orange bullets. You see that here I'm plotting a lot of circles, okay, a lot of bullets, and the bullets means that basically we are plotting the average relative errors for several values of the basis of the velocity basis, okay, so 30, 32, 34, blah, 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 50 basis. And we do the same also for, I mean, we do that for the EFR no EFR that are the full circles, and EFR EFR that are the empty circles here, okay? And then you have to draw a line that is the Pareto front. How can I draw this line? Being optimal means to be the element that is most to the left, okay? And this element has to be below all the other elements on the right. This means being optimal in the Pareto front limit of relative wall time and average relative error. So in this case, you see that the first element is of the EFR no EFR, okay, and it's not unexpected because EFR no EFR is faster because you are not, you know, solving the linear system and you are not combining the solution, you're doing only step 1. But then you see that you have to choose something that is below and to the left to all the other orange points. And the next one is that. So you have to choose something that is below and on the left on the other points. And you see that 32 now it's the optimal one, okay, and so on. So you see that on the Pareto front, that is the most convenient choice to obtain a good accuracy with respect to the time. Basically, you have always to choose EFR and no EFR. And this is both for velocity and both for pressure. You see that the green line is the Pareto front for the pressure. Okay, and even if I am increasing the wall time, so even if I am adding basis for the EFR, no EFR, I'm not reaching the accuracy of the other algorithm. Okay, so in this sense, EFR it's also convenient. Okay, from a computational viewpoint. Okay, here there are the force coefficients, and both are quite accurate, but EFR it's more accurate. We can see it in the lift coefficient, and basically the blue line and the green dot line coincide. Great. Now the natural question is like, why you were focusing only on half of the interval? The answer is we tried first to focus on the whole interval, and the results were somehow disappointing. And I'm showing you, for the sake of clarity, this fact. So once again, we have the relaxation. So actually the setting is completely equal, let's say, to the experiment 2, except for the length of the time interval where we are taking our snapshots, okay? And these are the bases that we are using. And you see that EFR is somehow off, okay, for the velocity, and both are inaccurate for the pressure fields, as you can see here. From the relative errors, we see that basically EFR, it's good for velocity in the first half of the interval, but then the two methods are comparable, and actually they reach pretty, pretty disappointing values for the errors, okay, as you can see also for the pressure. And you see that the lift and the drag coefficients are totally off. Why we are not accurate, with both the problems? Well, you can understand it if you look at the form simulation for t equal to 1 and t equal to 8. And you see that for the first half of the interval, you have something that is laminar, but then you have this kind of, vortex behavior. And the combination of that, it's really complicated to be recovered with POD. Okay, and so this is the reason why we decided to test our problem only on the vortex shedding behavior. Okay, and this is also the reason why I won't show you any more results about experiment 3. So from now on will be only experiment 1 and experiment 2. So now the other step that we took is about prediction. Prediction means that you are running your reduced simulation in an interval that it's not covered by the snapshot that you have taken in the offline phase. So for experiment 1, okay, we are predicting in future from 8 to 12, okay, having taken the information only from 0 to 8. And you see that we are pretty good, okay, in the errors. EFR it's more accurate. So EFR it's always orange in the errors. And you see that the orange line here for the velocity is good. And also for the pressure, overall, we are quite accurate, okay, even if in the beginning, EFR and OFR seems to be more accurate. But we have seen that for some time instances, EFR, no EFR in experiment 1 was better than EFR. However, overall, we maintain an error under 10 to the minus 1. Drag and lift coefficient, as I told you, it's very difficult to recover them even in the reconstructive regime. So you see that the lift is well recovered by EFR, the green dot line, but the drug, I mean, both of them are completely off. Now the question is how the relaxation impacts the prediction, right? So here you have the relaxation, and we try the prediction, okay, in this time interval here. And you see that basically both are inaccurate, and there is no convenience in using one or the other one, okay? Both in terms of relative errors, but also in terms of lift and drag coefficient. The next step that we took was about model order reduction, but also in the Reynolds number. So now the kinematic viscosity is no more fixed, and we applied a nested POD, okay, to reduce the dimensionality of our system. What does it mean? It means that basically you take a lot of time trajectories for several parameters, and you compress each time trajectory. Once you have compressed each time trajectory, you have a set of modes for each time trajectory, and you compress all this information that was already compressed once again, okay, in order to achieve a global compression for your problem. Great. I want to spend a little bit of time on why we choose this interval for the kinematic viscosity. So this means that basically the Reynolds for our problem will change in this value of parameter, in the sense that for each problem, okay, for each kinematic viscosity, you will have a Reynolds that varies in time from 0 to this Remax, and this Remax will be, you know, in this range of parameters. So why we choose that? We choose that focusing on the fact that we wanted that the solutions for all the kinematic viscosities that we chose, we wanted the solution to be somehow with a behavior that oscillates, okay? Because in experiment 3, we have seen that if you have laminar and vortex behavior together, you are not able to recover the problem. So in order to choose that, basically we computed the time average magnitude of our inlet condition, okay? And we choose the upper bound here in order to have this value of, let's say, average Reynolds. And this value is actually the value where the vortex shedding is happening for, you know, the steady inlet condition, okay? So somehow was a way to try to understand when the vortex shedding could happen, okay, in our system. Another thing that I want to stress is that here, in this case, delta, it's not anymore the Kolmogorov scale, but it's H-mean. This is another classical choice for the filter radius, because now the Kolmogorov scale depends on Reynolds, and you don't want, you know, delta that changes for every parameter. You want to be consistent in the choice of delta. So this is the MPOD, EFR, no EFR. So, okay, you apply this double compression and then you solve standard Navier-Stokes equation, or you can apply the filter also at the reduced level. Some results. So now we have Remax equal to 65. The setting is actually the same of experiment 2. So we always have relaxation here. But now we are trying to solve the problem where we will have Remax equal to 65. Okay. Here you see the parameters. So we collected the 2000 snapshots in this time interval for 20 parameters. Okay, the parameters have been chosen through log uniform distribution in order to have more information around the value of the kinematic viscosity that gives you high Reynolds number. Okay, so to be more informative for Reynolds equal to 100, basically. And these are the results. So EFR, it's quite accurate, both in velocity and pressure. We see that something strange is happening here, for example, for EFR, no EFR. Okay, so our solution seems more accurate for, you know, this time instance, t equal to 8. But in time, we see that basically we are always below EFR, no EFR with the relative errors. Okay, so you see in time we are always below, both for velocity and both for pressure. And here you have another Pareto front, and as you can see, the optimal choices are always the empty symbols. So empty circles for the velocity and empty diamond for the pressure in the EFR context. And here you see the drag and the lift coefficient. So for the drag, we are pretty good with both of them. Here we are off with both of the strategies. However, you see that EFR, that is the dotted green line, is somehow, you know, somehow is better in the representation. You see that the EFR, no EFR has huge oscillations here. Okay, so we are better in this sense. Now we are going to reconstruct Remax equal to 100. Here I'm plotting the solution for t equal to 7. So actually we are seeing another time instance with respect to experiment 2. And we are quite accurate with EFR, while with the no EFR, something strange is happening in the vortex shedding. And you see that EFR, no EFR has some problems also with the pressure. The data are the same of the other experiment, okay? So we took 2,000 time snapshots and for 20 parameters with the log uniform distribution. Relative errors, as I told you, with the velocity, we are pretty good, okay? For the pressure, we have a lot of oscillations, but still we are below the EFR, no EFR solution. For the Pareto front, except for the first 3, let's say, diamonds and the first 3 circles, then the optimal solution in order to achieve a good accuracy is always given by the EFR, no EFR strategy, okay? And here, once again, drag and lift coefficient, and we start to be really off with the lift coefficient. However, you see that the oscillation of the EFR, no EFR are really huge with respect to the EFR strategy. Great. What about prediction now? Prediction in this sense means actually to predict Reynolds. Okay, so we have seen that for experiment 2, we started to lose accuracy, okay, in the prediction of the future. So we decided basically to not predict the future, but to predict higher Reynolds, okay? So if the max Reynolds number is something like 110, we still are better in terms of relative errors. We are overall more accurate for both the variables. I'm showing you the drag and the lift coefficient, but now you have understand that basically it's almost impossible to recover these two quantities, okay? But what happens if I go further with the Reynolds number in the prediction? So I stress that here we are not collecting information for higher Reynolds, okay? So we are basing our prediction only on the snapshots that are from 65 to 100. Well, it happens that if you go further in Reynolds and it's not unexpected, basically you have no convenience in using one or another strategy, okay? So we are quite inaccurate both with the EFR and both with EFR, no EFR, as you can see here. Also the drag here basically is off, and the drag is usually recovered quite well. Okay, great. So this is a summing up of what we have seen, but actually we have seen that basically in reconstruction and sometimes in prediction, it's really beneficial to use EFR strategy. And EFR strategy is also optimal in the Pareto sense with respect to the time that you are consuming for the reduced simulation and the accuracy that you have. However, there is a lot of work that can be done on this topic. First of all, this is an experimental, let's say, experimental analysis, okay? So it would be of interest studying, for example, numerical analysis in order to understand what are the values of delta and chi that you can use in order to achieve, you know, some optimality in the error decay. And of interest, most of all for applications, can be also studying inconsistency with respect to delta and chi, in the sense that you can use some parameters, delta and chi, in the offline phase, but then maybe you can change delta and chi in the online phase in order to change the diffusivity at the online phase, because maybe the solution is it's somehow less oscillating or more oscillating in the online phase. And for sure, it would be of interest, you know, explore higher Reynolds number. We did some first tests about that, but I think that these two topics are somehow related, because for higher Reynolds number, you have somehow to change the values of the parameters also online to be more accurate. So that's all I wanted to say. So thank you for the attention.
Thank you, Maria, for the clear and interesting talk.
Thank you.
A virtual clap.
Thank you.
And if somebody has some questions, you can unmute yourself or just write them in the chat and then we read them. Well, maybe in the meantime, I have one.
Mm-hmm.
I was wondering when, so in a lot of test cases, they show that using the same numerical scheme with the same stabilization or whatever, or in general the same numerical scheme also at the reduced order level is useful to, it's necessary to maintain good accuracy.
Mm-hmm.
So what are the cases when this is not needed? Because now you compare the when it's needed and when it's not.
Mm-hmm.
But is it actually? I mean, is it true that in general you can always assume that being consistent with your numerical scheme is necessary?
I mean, this is
also the ROM level.
This is not true, in the sense that there is a lot of literature about inconsistent stabilization, okay? In the sense that you use stabilization and then you can apply standard, let's say, I'm talking about Navier-Stokes equation, but this is, I mean, a general comment on PDEs that need stabilization, okay? It's, the world is full of literature about inconsistent stabilization, okay? And they actually, I mean, work in the sense, if you have a problem like that, okay, you see that EFR, no EFR actually works fine. So somehow, sometimes they do not use also the online stabilization. I think because, you know, coding also the online stabilization is heavier, okay, and you want to be fast. However, here we are doing really a better job, okay? And here we also show that actually adding the filter and the relaxation step also online, it's not a big deal in terms of computational cost, okay? So it's always, you know, a trade-off. I mean, it seems that being consistent, it's always, let's say, beneficial if you take, you know, your data in a certain way, if you don't go too far with the prediction, okay? And if your problem is somehow, let's say, well posed for the reconstruction, okay? Because we have seen also that for experiment 3, where is here, we had really, you know, here there is no, it's not beneficial at all, okay? So for sure, you have to analyze your problem, understand that if it's convenient to use also online, okay, your stabilization, because this kind of regularization is quite cheap, but there are stabilizations that are, you know, more expensive. And then in that case, for sure, let's say it will be beneficial, okay? But it's always a matter of trade-off somehow. I don't know if I answered your question. So it's not really necessary, but it depends if you want to be more accurate, paying some, you know, some costs online.
Yeah, of course there is a trade-off with the accuracy. Yeah, maybe it was more, this, but also maybe I was wondering when maybe they give the same results. I mean, the gain in accuracy is not that's much significant to use it. I mean, I was just wondering this because I mean, I saw always comparisons where the being consistent is always helpful. So
I mean, when I think that it's not helpful when actually your POD, your system, it's not representing well, you know, the problem. In this case, both are inaccurate, okay? Because the combination of the two strategies, the two behaviors, somehow it's really difficult to be recovered with the POD, right? So if the POD is not well representative, no matter if you are doing stabilization or not, you are somehow losing accuracy with both of them. I think that this is related, you know, it's related to the construction of the spaces somehow.
Yeah, thanks. Thank you very much.